In this section, we're going to discuss the wave-particle nature of light. So photons can be viewed as particles of energy. And we also know that light has wave-like properties. And we discussed wavelength and frequency. So this leads to a dual nature of light. And we can say that light behaves as both a wave and a particle. And this was a pretty puzzling thought for most scientists at the time who were trying to define some of these properties. Some argued, hey, light behaves as a wave. Others say, no, light behaves as a particle. But in reality, we have this wave-particle duality, which makes the properties and analyzing photons of light very, very, very difficult to characterize. So we looked at the electromagnetic spectrum, and if we look at a prism of white light, we see this rainbow of colors, and we see this spectrum looking at all the wavelengths of visible radiation. But if we took a tube of gas and we excited it with a photon of light, we're going to see different colors. And in gases, we do not see a spectrum of color. The color appears as lines of specific wavelength. So this is different than white light because we're now seeing lines of specific wavelength. We know that wavelength is related to energy, so chemists at the time were really trying to work on how they could put a relationship together to relate the energy to lines in these line spectra. So in 1885, a man by the name of J.J. Balmer related energy to the lines in a hydrogen gas spectrum. And the relationship that he came up with was 1 over lambda is going to equal 1.097 times 10 to the minus 7 meters to the minus 1 power times 1 over 2 squared minus 1 over n squared, where n is an integer equaling 3, 4, 5, and so on. And by choosing a value for n, the wavelength of a line can be calculated. And in these line spectra, we can observe that they're different colors. And we should be able to then relate the wavelength to the color of light that we observe. So, for example, if we looked at n equals 3, what we can say is that 1 over lambda is equal to 1.097 times 10 to the minus 7 meters to the minus 1 times 1 over 4, which is 1 over 2 squared, minus 1 over n squared. N is 3, so n squared is going to be 9. And if we do this math, we get 1.524 times 10 to the minus 6, or sorry, 10 to the 6th meters to the minus 1 power. So if we would then calculate lambda, so 1 over lambda is 1.54 times 10 to the 6th, we get 6.563 times 10 to the minus 7 meters, which, if we convert to nanometers, is 656.3 nanometers, because 1 meter is 1 meter is equal to 1 times 10 to the 9th nanometers. So doing that conversion gives us this number right here. And when we look at these different lines in the hydrogen spectrum that occur in the visible region, we refer to them as the Balmer series. So what this does is, when we look at the line spectra for hydrogen gas, we can now see 3 lines, and we can, or some people's eyes will see 4 lines, and we can correlate them to wavelengths of light. In this case, this line right here would be 656.3 nanometers, and we can use Balmer's relationship here in order to calculate those. And physicists at the time observed line spectra for the elements, and they have this equation right here for calculating the wavelength of hydrogen, but they couldn't relate any of this to any physical ideas. And it became very frustrating for these guys until a guy by the name of Niels Bohr came along and came up with the Bohr model for the hydrogen atom. So that's what we will talk about in the next video.